Let's analyze this algorithm. What we want to know is, how much work is it going to take for us to complete this algorithm? How many operations are we going to do? And how many steps is that going to take? So the analysis is straightforward. For either flavor, inclusive or exclusive, for each of the n iterations of the loop, we take one step and we do one operation. Thus, we require n operations to complete the algorithm, and we also require n steps. But the parallelization of this algorithm is more complex than with reduce. With reduce, it was really clear that the different pieces of the computation tree could be computed in parallel. With scan, this is much less clear. So the questions you should be asking yourself now are, A, how do we compute scan in parallel at all? And B, how can we reduce the work and step complexity of a parallel implementation as much as possible? But even before we get to those two questions, let's answer a larger question. Why do I care about the parallelization of scan in the first place? So here's a high-level intuitive explanation. Many computations have the following form. We want to process a list of inputs, which I'm showing here with blue circles, and create a list of outputs, which I'm showing here with red circles. And we begin by computing this first output from this first input. Then we use that first output and the second input to compute the second output. Use that second output and the third input to create the third output, and so on. For instance, in our checkbook example, we use the previous balance and the next check amount to compute the current balance. This creates a dependency structure that looks like what I've drawn in green. When we structure our computation like this, we see that it has no apparent concurrency. We're only doing one operation at a time. First, we compute the first output, and then we use the first output as an input to get the second output. We use this output to get the third output, and so on. Now, this is a very serial structure, and if we implemented it in this way, it would be a poor fit for a GPU indeed. Computations like this can often be expressed as a scan. And if we can characterize our computation in terms of scan, that's great, because let me tell you a little secret. We can parallelize scan and make it run fast on a parallel processor like a GPU. Now, not all computations with this sort of dependency structure will fit into the scan model, but many will. And for those computations, leveraging an efficient parallel scan implementation turns the problem from something that would be a poor fit for a GPU into something that is now a much better fit. So, how do we parallelize a scan computation?